Alright, what's up, guys? So, today we're going to be delving into the textual n-gram abbreviation. Before we do that, I'm just going to give a quick, warm up, or I guess a refresher on what we did with hard prompt compression. We know it's a way of removing tokens from your prompts to allow for the overall context. To allow for the overall context window to be shortened. Now, the way you can do that is threefold. There's three different ways. You first have your static self information, okay? And the way this works is first by constructing a large corpus of text. This just means a large body of text, which is found through various sources. In this paper, they use Wikipedia, ShareGPT conversations. Just for context, because I don't think I've given it before, ShareGPT was a service where you could share your ChatGPT project, your ChatGPT chats, right? However, now this is built in, so you don't really need this anymore. So they deprecated the project. So as you can see,
hits or take this next stress apart from slightly different. But if you but this is feedback.
This was the way you could do that, right? But anyways, so that's it. Share GPT conversations, and then archive articles as well, like this one that I'm reading here. That's just where you could post your research papers. Okay, cool. So you have this huge, vast amount of text. Now, what we do with this text is we first tokenize it, right? So it becomes tokens. And then we're going to compute the unigram frequency, the unigram frequency for every token shown. So what that means is that in your prompt, right, let's say you have 2 words only in your prompt, just for simplicity. Let's say it was the car, right? So what the hard prompt compression will do, specifically the static self information, is it will take the token and then the car token, and it will put it in this specific algorithm. What this basically does is it takes the token t, let's say it's the, and it will loop it through each and every token within the corpus that you've built. And if it finds the same token within that large corpus of information, well, then it increments a count. And that's one frequency that we see, right? So for example, in the corpus of text, if there was 300 instances where the was shown, well, that means your unigram frequency is 300. And that is what we actually put into our self-information score, which is not really information in the sense of like knowledge, but rather it's information which is new and novel, right? So the more informative something is how rare it is, how not seen it is, right? In the case of that's probably not going to be the case, because the is seen a lot within the English language. So that token is probably going to be a lower scoring token. Car, also going to be vastly seen because it is a noun. However, it's not going to be seen as much as the. So it's still going to be on the low end of the tokens, but not as low in terms of informative compared to the, right? And so that's how this works. Basically figuring out how frequently you see a token within a text body that you have, and then using that within the self-information score to determine how informative your token is, which is just how rare your token is. The obvious issue with this is that it doesn't take into account context. It uses a global standard for what your text is. However, the actual benefit to static self-information is that it is able to actually use a more simpler way of computing things, right? It's not using complex algorithms. It's not using a lot of computation. It's very simple for loops, and obviously now with like the way that computers have progressed, using those for loops at scale isn't that big of an issue. So static self-information thrives in the fact that it's easy to scale, and also it's very, very easy to implement, right? You don't really need too much to get started, and you don't need too much compute. Now we move on to dynamic self-information. So this really just addresses the issue with static self-information in that now your tokens are context aware. Well, they were always context aware, but your self-information score is context aware. And how we do that is by taking a token and feeding its preceding context. So it's preceding like set amount of tokens into a pre-trained LLM. And when you put it into this pre-trained LLM, a probability distribution will spit out. And within that probability distribution, there will be your target token. And what you're essentially going to do is see how likely it is for your target token to be the next token, right? And so you just, essentially what you do is you take that probability distribution, find your target token, and then there'd be a probability score attached to it. You take that score, which is what the model probability is, and then you use that within the same formula, because this is your probability, and in this case we're just using it as unigram frequency. But you're going to take that model probability, plug it into this formula, and you're going to get your dynamic self-information score. In this case, you're still finding how rare this token is going to be, right? And the more rare it is, obviously the more informative it is. However, now you're integrating a context-aware solution because you're using an LLM which has self-attention layers that are able to capture context. Then we have combined scoring and phrase level pruning. So this is where you integrate, it's basically a hybrid. You integrate both your static and dynamic measures, okay, or dynamic self-information scores. And it works like this. You're first going to figure out whether the both of the scores are similar to one another. And you do that by using this formula here. When you subtract dynamic from static, you use the absolute value over the static, you'll figure out the relative difference. Now, if that relative difference is under 10%, that's what they found through empirical observations. If that relevance is 10%, well then you can use the arithmetic mean of both scores. What this does is it essentially finds the average of both scores, and this way you're able to reduce variances, right? Because both of these scores are going to have some noise in them, right? Some random errors that occur just because of the process of you know, the computation, right? It's just a natural thing that occurs in mathematics, having noise, random variances. Now, to avoid this or to lower these noises, if you use two scores and the combination of both in terms of an arithmetic mean, you'll be able to cancel out some common shared noise between those two scores. And this will allow you to have a more accurate and reflective score for your self-information. So that's sort of the reasoning behind using the arithmetic mean. But you can only do this if both of the scores are relatively the same, and that's why we use the relative difference. However, if the relative difference is huge, which is above 10%, then you're better off using the dynamic score, which is why in this piecewise function, you have a condition where if it's under 10%, then we use the arithmetic mean. But if it's over, then we're going to use the dynamic scoring because that is just much more reliable. Okay, so that's the logic behind this and what this over here means. Not too hard, but just understanding is very important. So this is the approach, the hybrid approach of using both dynamic and static self-information scores is how the compact prompt framework works, because that is the most accurate score you can get. Okay, cool. Now we move on to textual n-gram abbreviation. This is an approach which is not necessarily part of prompts, right? Prompts, because in this case, the hard prompt compression, this was solely optimized for prompt compression. However, in my agentic workflow, I have large amounts of data files coming into the flow, right? And as such, I need a way for me to basically compress those textual files so that they can actually be used in a way that will not lead to context rot within my LLM brain. So textual n-gram abbreviation is a way for us to actually implement that. Implement this into data files to essentially allow the LLM to still understand what the data file means, but reduce the overall amount of tokens that it consumes. So here it is. N-gram abbreviation uses a method similar to LZW, Lempel-Ziv-Welch algorithm, that compresses text by losslessly replacing common sequences with short human-readable tokens. So you can search, index, or apply natural language processing (NLP) directly on the stream without full decompression. It delivers substantial size reduction with simple table lookup encoding, more transparent and lightweight than heavy binary compression like ZIP or BZIP2, and reversible unlike lossy embeddings, and minimal compute costs. To compress attached text, we employ a user-configurable n-gram abbreviation pipeline. Okay, so there was a lot that was said there. And essentially what this is giving is just context as to what the textual n-gram abbreviation strategy will do, right? And in our case, what it does is some of the common attributes that it has with LZW, which is another algorithm, is that it's lossless, which means that you can always revert back to your original work without any issue, right? So this differs from like many other approaches in reducing data size, because when it's losslessly, you can easily revert, right? And the reason for that is because it's essentially creating abbreviations, right? As it says, it's creating abbreviations. So when it creates these abbreviations, it's going to have like a lookup table or some sort of way for us to reference what those abbreviations mean. So you can always just look at that lookup table and just easily revert back to the actual meaning of that abbreviation. At least that's what I'm thinking right now. Obviously, I need to read more and understand it a bit more before we can move on from that understanding your mental model. But based off of the context given, that's what I'm thinking. Cool. Okay, so let's put this into Claude just to see if we're not missing anything important. Cool. Oops. Fair. Okay. So I'm not gonna give too much importance on that. Okay, we get it, bro. Goddamn. Will this like ever go away? Can I just like remove this? Yeah, I'm just gonna remove it. Sorry guys. Hold on. I'm just gonna remove Voquil because I don't need it. I have Whisper Flow. So applications. How the hell do I remove it? Oh, I have to go to Finder. Application. Voquil. Nice. And move the trash. What the hell? Option, command escape. Okay. Option, command escape. Bro, it's not even here. Alright, whatever. Okay, sorry about that, guys. Okay, let's continue. Okay, so this is just giving us the context as we said before. So now what we will do is we will move on to the extraction and frequency analysis. Cool. Okay, so extraction and frequency analysis. First, the user specifies an n-gram length, n, commonly between 2 and 5. We extract all n-grams from the document corpus and compute their frequencies. These frequencies are visualized in a histogram, enabling the identification of the top k most frequent patterns, typically k equals 500 to 150. Okay, so n-gram length basically just means a consecutive amount of characters or tokens in this case, I guess. So I do have some questions about that. Actually, so let me actually just like go ahead and bring this into Claude. I think ChatGPT voice would actually be much better for this. I like the voice feature. Okay. Let's see here.
Hi, glad to meet you. Exactly. So the idea is that once you pick your n-gram length, like for example 3 for trigrams, you scan through your whole corpus and count how often each of those n-grams appears. Once you have the frequency counts, you plot them, often a histogram, so you can see which patterns pop up most often. And from there, you usually take the top K patterns, like you said, maybe the top 100 or 150, to focus on the most prominent ones. It's a super useful step for discovering common phrases or structures in your text.
I see. What I'm a little bit confused about is what exactly does n-gram mean? Does that mean just an n amount of consecutive tokens, words, characters? And also, when we talk about using the corpus and counting how often these n-grams appear, as I said before, if I don't know if it's a token, like if it's consecutive tokens or consecutive characters, I won't exactly know what the whole corpus is talking about, right? Also, how exactly does the frequency work? Is it a unigram frequency that we use?
Ah, yeah, great question. So first off, an n-gram is basically just a sequence of n consecutive items. And yes, those items could be words, so you count sequences of words, or characters, so sequences of letters, depending on how you define it. If you're not sure, it's good to clarify whether you're working on word-based or character-based n-grams, because the meaning changes. Now for the frequency, once you've defined your n-grams, you count how many times each one appears across the entire corpus. A unigram frequency would just be counting individual words, so how often each single word appears. Once you go to bigger n, like bigrams or trigrams, you count those whole sequences. So yes, you'd compute a frequency for each n-gram type, and that gives you a sense of which patterns dominate your text.
So we're essentially taking each of the n-gram, the n-gram, I guess, characters that we have, all the unique ones, and then we're putting it through the same corpus, or are we putting it through? Oh, okay, I understand. So we first figure out all of the n-gram frequencies which have occurred within the text. Then we deduplicate them because you could have duplicates. You take all the unique n-gram frequencies and you put them through the corpus of text to figure out which of these n-grams can be abbreviated using an acronym. For example, the trigram of United States of, or sorry, the bigram of United States will usually be abbreviated to US because that is the pattern that we see the most. So we're essentially figuring out how many times these n-grams appear within the corpus of text given. And then we use that as a justification for actually abbreviating some of these as they happen so often, it's pretty normal. And the model will understand, like the AI model will then understand what those abbreviations mean logically. So, yeah, I guess that makes sense. But um, how do we know? How do we know which n-grams to abbreviate? Like, it's very vague to say that, you just abbreviate the frequencies which happen the most often. How do we know or define what happens most often?
Ah, that's a great point. So it's kind of a threshold decision. After you plot the frequencies, you choose a cutoff. Sometimes it's a top percentage, like you might say anything that falls in the top 1% of frequencies. Or you could use a statistical measure like a z-score, or look for a natural break in a histogram. Basically, it's a balance between being common enough that it really stands out, but not so common that it's just a generic word. Once you set that threshold, it gives you a clear rule for which patterns get abbreviated.
Can this process be automated so that when we have data documents which are being posted through an agentic workflow, I don't have to do any of this histogram plotting or any of this myself. Instead, I could just have an algorithm which it goes through, which the specific text goes through to get abbreviated by whatever n-gram I choose. Let's say trigrams. So every three tokens or characters I would do maybe. It gets abbreviated, or sorry, it doesn't get abbreviated, but it gets clustered together so that when we actually put it into the algorithm, it will look for those specific words as patterns that happen, and then based off of that, we know which of the trigrams to abbreviate.
Yeah, absolutely. You can definitely automate this. Basically, you'd write a script or use a pipeline in your workflow that as soon as a new document comes in, it tokenizes the text based on your chosen method, like words or characters. extracts the n-grams, counts their frequencies, and compares them to a preset threshold. Once it identifies the top patterns, it can flag them for abbreviation. You can even integrate it with something like a rule-based system or a machine learning model, so it learns better abbreviation patterns over time. So once it's set up, it just runs in the background, and you don't have to manually intervene.
Cool, so I understand. Cool, so I get what's happening now. Essentially, the extraction and frequency analysis is basically the user first has to specify an n-gram. That's just a set amount of tokens or words or text which need to be consecutive with one another. So, for example, you could have a bigram, which is two things that need to be one after another. So, something like United States would be bigram, right? Because United and States are two words that happen one by one, right? So that's what the n-gram means. And it is commonly between 2 and 5. So I would probably pick the median or like the average of that, which is 3 for a happy like medium, right? Then we extract all the n-grams from the document corpus. So that is the document corpus. Once we have done that, we are going to compute their frequency within that specific document corpus, now that I'm reading it. So it isn't a global corpus that we are generating. Instead, we're just essentially taking the document corpus that we have, right? We're figuring out all the n-grams which are possible, which is just basically taking whatever n equals. Let's say it's 2, so you're taking each 2 words, and so after every 2 words, you're just making new n-gram sequences. And you're taking these sequences and you're going to then compute how frequently they occur. So, for example, let's say United States was one frequency. So, or sorry, one n-gram, n-gram instance. So then in the whole document, you're going to see how many times you see United States. And if it's a large amount of time, which can be dictated by an actual threshold, let's say the top like 2% of n-gram of n-grams are actually going to be abbreviated. So that's how you know which of the n-grams are going to be abbreviated, by just figuring out how frequently they occur and then figuring out a threshold and saying that oh, anything above this threshold is going to be what is going to be abbreviated. And then you have a dictionary construction. So we assign each of the top k n-grams. So okay, I see. So that's what the top k means. So we're basically figuring out you don't need to necessarily visualize them, right? That is just something you would do if you're doing like a manual workflow of textual n-gram abbreviation. However, I would assume that this would be most useful when it's not necessarily a thing that we use for like manual usage. Like it's something that is used for the actual automation, right? We're going to use this automated. But anyways, these frequencies are visualized in a histogram, enabling the identification of the top k most frequent patterns. So that top k is just a variable of k, which is between 100 and 150, and anything that, so let's say k we define as 120, that means the top 120 of these n-gram patterns or instances are the ones that are going to be abbreviated. They're going to be abbreviated, right? So the top k amounts are going to be abbreviated, and we know that these are the top k by computing their frequency within the document corpus, right? After extracting all of the n-gram instances. Then we have a dictionary construction. So we take this top k amount. I said that k was 120. So let's say top 120 n-gram, again, k could be anything. Typically, again, it's 100 to 150. That's just like the industry standard. So we assign each of the top k n-grams with a unique placeholder token. So ABC1, BD2, so it's basically just some random placeholder token. This mapping is stored in a metadata table, ensuring lossless round-trip reconstruction. Okay, and so in this case, we're just basically making note of what the top K n-gram patterns are, and then we're just assigning each one with like a unique placeholder token, right? This placeholder token doesn't really have that much significance. It's just random strings of text, is what I'm assuming. So let's see that though. So basically what it's doing is it's taking all of the top K n-gram patterns and it is computing a unique placeholder token which doesn't really have that much meaning. It's just used as a way of tracking all of these specific top K patterns, and then we store all of this in a metadata table to use within the next step of our actual process. What I'm basically asking you is that, is there like an algorithm or a concrete way of figuring out what the placeholder token should be, or is that just randomized?
Great question. So it's not just random. There's usually a systematic approach. Often the placeholder tokens are just assigned sequentially, like top 1, top 2, top 3, and so forth. So the mapping is easy to generate and track. Another approach is to use some deterministic pattern like a hash to the n-gram or a fixed prefix plus a number, just so that the token is always unique, but it's still human readable. The important thing is consistency. Each top n-gram always maps to the same token, so that when you decode, you know exactly how to get back to the original text. So while it's not random, it's also not super complex. Just a predictable scheme that your process follows each time.
Okay, so basically what you're saying is that it doesn't necessarily matter which token is assigned to the n-gram pattern. However, it matters how those tokens were built. If they were built using a systematic approach, then that's good because it ensures that each of these tokens are unique and not duplicates of one another.
Exactly. Nailed it. The meaning or label of the token itself isn't as important as the consistency of the process. As long as each token is uniquely and systematically assigned, so no collisions, no accidental duplicates, and the decoding step will always work reliably. That systematic approach means you can scale it up to large corpora, and the mapping is always predictable. So yeah, the key is that systematic generation method, not the specific token labels themselves.
Okay, cool. I understand all of that, so thank you. However, what exactly does a large corpora mean?
Good question. So a large corpora, that's just the plural of corpus, basically means a really big collection of text data. So instead of just a few documents, you're talking about tens, hundreds, or even millions of documents, all together as one big data set. And when you have a large corpora, it just means you get these super frequent patterns, more statistically significant results, and it really gives you a robust basis for these kinds of analyses, especially if you want to automate it across a huge range of texts.
Okay, cool. So I understand exactly what's happening here. So essentially, we're assigning the top K n-grams a unique placeholder token. Now, this placeholder token doesn't necessarily matter. The actual token which is assigned to each of these n-gram patterns, it doesn't really matter. However, the way that you build these tokens does matter, right? Because each of the tokens that are given to the n-gram patterns must be unique. So you need some sort of systematic approach to ensure that all of them will be unique. And one of the ways of doing that is by sequentially assigning tokens. So you have like token 1 be for the n-gram pattern of United States, right? Or in that case, it would be bigram because it's 2, right? And then placeholder token 2 would be associated with the n-gram or the bigram pattern of the Canada, right? Let's say that's like seen a lot in the document corpus, the Canada, right? So that's what happens, okay? And the reason why we do this is because then we take all of these mappings where you essentially have a key value store, right? Your key is your token, and then the value is the associated n-gram pattern, and you're going to store this in a specific table, right? It doesn't really matter where the table is, but you need to store this in a table so that you actually have a lossless reconstruction. Because now you're actually storing where each of these n-grams, which are going to be changed, right? Each of these n-gram patterns are going to be changed to something else. You still have a record of the original n-gram, right? Because of this table. Okay, then the final step in this whole process is going to be contextual replacement and reversibility. We replace every occurrence of the most common n-grams with their placeholder, taking care to resolve overlapping matches and preserve punctuation. At downstream stages or upon user's request, placeholders are substituted back to original n-gram using metadata table, guaranteeing exact reversibility. Okay, so we're essentially using this placeholder token. Again, it doesn't really matter how it's generated, but we're using this token, a little different model than I was thinking, but you're using this token, and when you actually need to use I guess, this data document, you just take that token and reverse to figure out what the n-gram is, right? And so that way, when at downstream stages, so when we actually need this document, you can actually have the proper document which is used. However, I wonder how exactly does this reduce the context size, because when the user actually uses it, the placeholders, which are the ones in the metadata table, are actually removed and replaced again by their original n-grams, which makes sense in this case because, for example, the token of ABC1 doesn't really mean, or at least the model doesn't know that means, for example, United States, right? It doesn't really know that unless you give it some sort of context, which we're not in this whole design. So it makes sense why we're essentially reversing it back to United States so that the model actually knows the actual meaning of that specific placeholder token. However, in that case, you're just bloating it back to its original context size. You're not really reducing the tokens. So how exactly would that work? Let's see here. So I'm just going to take the whole thing and paste it into ChatGPT, and then let's just ask it, let's have a conversation with it, basically. I'm going to do it in a new chat. My current confusion is that if in the decompression we are actually reverting this back to the original n-gram patterns, how exactly is there going to be a reduced context window and reduced data file size? Because we're using this in an agentic workflow. So if in the time where the document is actually processed within the LLM, we're bringing it back to its actual original state, how exactly are we reducing the total amount of information or the amount of tokens which are present in that data file?
That's a really good point. The size reduction benefit actually comes from how the text is stored and processed before the LLM sees it. In other words, while you're decompressing it at the end to fully restore the original text, the bulk of your LLM pipeline is working on the compressed form, which is shorter. So you're reducing the number of tokens that the model needs to process. The context window is reduced because the same patterns are represented by just a single token. So the LLM is still working on a smaller number of tokens, even if you decompress later for final output. Does that make a bit more sense?
No. how exactly is the Ngram abbreviated uh, document used within an LLM workflow? Could you just explain that a little bit more? Use some research. Don't just say it off of the top of your head. Use web search tools to actually find real documents from developers and engineers to help me understand this.
In an LLM workflow, ngram abbreviation is applied during pre-processing. Frequent sequences of words, ngrams, are replaced by short tokens, reducing the total number of tokens. The LLM then processes this compressed form, which allows for a larger context within the same window. After the LLM completes its task, a post-processing step restores the original sequences using the stored dictionary, ensuring no information is lost.
But how exactly does the LLM understand the abbreviations? Because in the paper, what it said is that when we're actually building the dictionary, which includes the abbreviations and mapping those to the ngram patterns, those tokens just need to be unique placeholder tokens. It doesn't necessarily really matter what they are. Uh, all that matters is that you have a systematic approach in assigning those tokens so that you don't have the same tokens for two separate ngram patterns. So in that case, the LLM doesn't understand that context because it wasn't really given to it. So how would it know that, for example, the token of ABC1 correlates to United States?
When you use placeholder tokens in an LLM workflow, the model treats them just like any other token. There's no built-in understanding of their meaning. Instead, the LLM processes them as rare words, so you reduce the overall token count, but don't give the model special knowledge. Afterwards, you rely on a dictionary to decode these placeholders back to the original phrases, ensuring that the final text.
What I don't understand is how exactly will an LLM know that, for example, the placeholder token of ABC1 correlates to United States? Because it, as you said, it doesn't have a built-in understanding for the tokens, which is fine. But at least it maps those tokens to an embedding vector, right? The embedding vector for ABC1 is going to be vastly different for the embedding compared to the embedding vector of something like United States. So how exactly does the model understand these abbreviated tokens?
In a typical workflow, when you use placeholder tokens from an ngram abbreviation, the LLM just treats them like any other rare token. The model doesn't inherently know that a placeholder like ABC1 means something like United States. Instead, it embeds the token base purely on its occurrence, so its vector is different from the original phrase. Thus, the model uses the placeholder for token efficiency, but it doesn't understand its meaning unless you fine-tune the model or guide it with examples.
So then, when we're processing this ngram abbreviated document within an LLM, how exactly will it understand these abbreviations? Because if those abbreviations mean something vastly different from their original ngram pattern counterpart, it's going to change the actual meaning of the document which is being given, and therefore the quality of the output from the LLM will be degraded.
To make placeholder tokens work in an LLM workflow, you need to guide the model by explicitly providing the mapping between placeholders and their original phrases. Without this, the model just treats the token like any rare word, so its meaning can get lost. By including instructions or examples in the prompt, like explicitly stating the meaning of each token, the model can better align its responses, ensuring the final output stays accurate and meaningful.
Okay, so this isn't really helping too much. Let's see if there's a YouTube video which allows us to understand. Oh my god. Okay.
can simply call me Joe, and super awesome that you're here today. I've been working as a software engineer for more than 15 years, and I switched to data science and data engineering about 4 years ago. And I'm here to share a few little things that I've picked up along the way with you. And today let's talk about natural language processing, also called NLP, and let's talk about n-grams. What are n-grams for, and what might be some problems with n-grams? So let's dive into it. How does basic text processing even work? Since machine learning models can't do anything with words, they need numbers. So the first step is we need to translate the words into numbers. This is usually done using a back of words approach, where the corpus is separated into words, and every word that is in this corpus gets assigned an index. So a word like this might have the index 1,
messages coming through, so I'm just gonna go ahead and switch off my screen. All right, so I realize now that this is probably not going to be the best. Uh, this is probably not going to be the best approach because I'm looking at the issues with it. Mainly the reason why I say that is it isn't really the best approach, and that's why I'm making a tweet about it. The reason why is because of the fact that it leads to degraded reasoning, right? I don't know how exactly we're going to be getting the unique placeholder tokens. It doesn't really talk about that. It's really just saying, oh, make a random unique placeholder token and then use that within your LLM workflows. There's two issues with this. The first one, if you keep that placeholder token and you just process your document with that placeholder token, well, then it's going to lead to reduced quality within the LLM because it doesn't really understand what the true meaning of this placeholder token is, which is the n-gram token or the n-gram pattern. And in the opposite direction, which is when you decode these placeholder tokens when the LLM processes it, then there isn't really a point in having this whole architecture, right? Because at the end of the day, when the LLM does process it, where the token count really matters, you're anyways using the original piece of external data attachments. You're using the original data size. So it really makes no sense in using n-gram abbreviation. And that's why I'm going to try to find another approach within context compression. I'm sure there are many, for specifically external data attachments. If not, I guess we're going to make one today. Okay. Cool. Let's hop on Whisper actually. Whisper Flow. I love this piece of software, I can't lie. I mean, yeah, I agree with the fact that their hard prompt compression was actually a really good idea. Using, a blended approach to avoid the noise within the score that's being generated. That's actually a really smart idea, but yeah, they kind of fell through with n-gram abbreviation. So let's see if we can find something else, to be honest with you right now. That is a bummer. Hello? Great.
And there's currently extensive conversation about how context is managed within agentic flows. In this video, we will explore the role of context in an agentic system and discuss strategies for effectively utilizing it. To get started, let's look at what we think of as traditional OAuth systems and traditional context. And when we think about this, we really need to kind of start with a definition. And it really is about, you have a user, an app. So this is very specific. We're working with an application, and we want to grant it permission to act on our behalf, the user's behalf, and this is critical during a single login. In other words, we want to grant permission for an application to do something on our behalf, but during a single login. So let's draw this up. Let's just kind of take a view of how this looks. So we have a user. They're interacting with an application. And somewhere along the way, there's a resource that they're trying to tap into. And then, as I mentioned, we have this authorization that happens. So let's just do a quick example. I have some application that want to interact with my bank, but I don't want that application to go actually connect to my bank and do stuff. I want to give permission for that application to actually use certain features of my bank so that it can go and buy stuff, perform transactions. So we do this thing where I kind of trust who I am. I say who it is, who I am. I interact with my application. I allow things to happen. I allow this to go and interact with the resource. And this all happens by we issue a token. That token represents me. It's something I've authenticated. And within that token, there's a set of scopes that say what I allow, what I am giving permission for this application to interact on my behalf with a resource and do read-only, read banking information, whatever it is that it needs to do. So this is what we look at when we think about more of a traditional context. And we can kind of break this down and think of it as there's who, which is the user. There's the what resource, so what am I trying to connect to? And there's also the conditions, which in the case of OAuth, this is the scopes. What specific action am I saying that this system is allowed to perform? All right, so this is what we think of in terms of traditional OAuth flows and context within that. The context is the who, the what, and what am I trying to do, what am I allowed to do. So let's talk about this in terms of agentic system. And again, let's start with, a definition of what like agentic context then would be, similar to what we did with traditional. So this is about, really, it's autonomous because we have agents that are interacting, they're doing things on, thinking, performing tasks, figuring out stuff. It's also very dynamic. In other words, it's non-deterministic. To solve a task, an agent may do one thing one time and something completely different the next time, depending on what it is that it's being asked to do. It may talk to multiple systems, multiple agents. And it also does delegation. Has that as a model with multiple apps. So this is what starts making context more complex when we think about it in terms of agentic systems. It's autonomous, it's self-thinking, it's dynamic, it's figuring out how that flow is going to look. It's not just a single application with a resource, figuring out what I need to do. It's delegation, it delegates on behalf of me, it delegates down the flow. And there could be multiple applications. So let's draw this out as well. So we may have something here which we add, which is an orchestration. So we add orchestration in the middle of it. We may have another agent. There's agent 1. connecting to a resource. When we're looking, and that's our context, who, what, and what are we allowed to do? In the terms of agentic, now we have multiple systems. We have multiple agents, we have LLMs, we have all this stuff that now comes into play when we're thinking about what is the resource. And then finally, when we think about the conditions, then we're really starting to think about more of really fine-grained access, and it's very dynamic. We get back to this non-deterministic behavior that we're seeing in agentic systems. So this really starts expanding out what we need to think of when we start thinking about context in an agentic system. Well, the first thing you kind of do, so let's kind of go to our model now. Let's start thinking about this. First thing you really do when you're interacting with a system is you have a prompt. You're asking a task. I want to see the financial information for a particular region, for a particular piece of my business, and bring that information back to me. So we start and we look at this, as a prompt. And of course, the prompt is linguistic, right? It's in our native tongue and language. The LLM understands it and understands how it's going to route and get through the system. Now, because it is a multi-system environment, we have to really then start looking at the situational.
This is not really helping.
Sorry about the wait. This is going to be a bit of a strange session because there is a workshop component to this. So lead it like in the absence of information. So you need history as well leading up.
Yes, API, CLI, MCP.
Yeah. Point here is kind of a catch-all, but what's really interesting is though.
this is Lance from LangChain. You might have heard this term context engineering recently. It's a nice way to capture many of the different things that we do when we're building agents. Of course, agents need context, they need instructions, they need external knowledge. I'll walk through some interesting examples of each one with popular agents that we use frequently in our day-to-day work. And I'll also talk about how LangGraph is designed to support all of these. But first, what is context engineering and where did this come from? Well, Toby from Shopify had an interesting post here saying he likes the term context engineering. Karpathy followed up on this and offered a good definition. Context engineering is the delicate art and science of filling the context window with just the right information for the next step. And Karpathy's recently highlighted an interesting analogy between LLMs and operating systems, like the LLM is a CPU, context window is like RAM, or it's working memory, and importantly, it has limited capacity to handle context. So just like an operating system curates what fits in RAM, context engineering you can think of as the discipline or the art and science of deciding what needs to fit in context of, for example, each step. Conflicting information, or injection of a hallucination, which influences the response in an adverse way. And so for these reasons, context engineering is particularly critical when building agents because they typically have to handle longer context for the reasons mentioned above. Now, Cognition highlighted this pretty nicely in a recent blog post saying context engineering is effectively the #1 job of engineers building AI agents. So what can we do about this? Well, I've had a look at many different popular agents that many of us use day to day, thought about this a lot, reflected on my own experience, and you can kind of distill down approaches into 4 bins. Writing context, saving outside the context window to help an agent perform a task, selecting context, selectively pulling context into the context window to help an agent perform a task, compressing, retaining only the most relevant tokens, and isolating, splitting context up, again to help an agent perform a task. And I'll talk about some examples of each of these categories. So writing context. Writing context means saving outside the context window to help an agent perform a task. When humans solve tasks, we take notes and we remember things for future related tasks. Well, agents can do those same 2 things. For note-taking, agents can use a scratch pad. And for remembering things, agents can use memory. So you can think about scratch pads as kind of a term that captures the idea of persisting information while an agent is performing a task. And I'll give a good example of this. Anthropic's recent multi-agent researcher, the lead researcher begins by thinking through the approach and saving that plan to memory to persist it. And this is a great point. You want to keep the plan around. The context window might exceed the limit of 200,000 tokens, but the plan can always be retrieved and retained. Very intuitive example of taking a note and saving it in a scratch pad. Now, I do want to make a subtle point. The implementation for a scratch pad can differ. So in their case, they just save it to a file. But you can also, for example, save it to a runtime state object depending on what agent library you're using. But the intuition is really that you want to be able to write information while the agent is solving a task, so the agent can then recall that information later if it needs. Now, memories are a bit different. Sometimes we want to save information across many different sessions with an agent. So typically, scratchpads are relevant only within a single agent session. An agent's trying to solve a problem, it'll use a scratchpad to solve the problem, and then the scratchpad's not relevant anymore. Memories are things that you want the agent to retain over time, over many sessions. So there's some fun examples from the literature. Generative agents, for example, synthesize memories from collections of past agent feedback. And you've seen this. ChatGPT has a great memory feature. Cursor, Windsurf also will auto-generate memories based on user-agent interactions. So this pattern is certainly emerging with popular AI products. And again, the intuition is pretty clear here. You have some new context, you have some existing memories, and you can update memories with new information dynamically as the agent is interacting with the user. Now, we covered writing context and talked about a few examples of that. Now let's talk about selecting context. So selection means pulling context into the context window to help an agent perform a task.
Hold on, before we move forward, I actually want to see something. Okay, perfect. So if I look in my code right now,
Now, we kind of talked about this previously, the scratch pads. Of course, an agent can reference what it wrote previously. This could be via a tool call. This could be by reading directly from a state object. Now, memories are a bit more interesting and a bit more subtle. There's different types of memories you might want to pull into context depending on the problem you're trying to solve. Could be few-shot examples that provide specific instructions for a desired behavior. It could be a selectively chosen prompt for a given task. Could be facts. And these are different memory types. Semantic memories in humans, for example, are things like facts, things that I learned in school. Episodic memories are more analogous to few-shot examples, past experiences. Procedural memories are like instructions, instincts, motor skills. And these are all things that we may want to selectively pull into context to help an agent solve problems. Now, where do these come up practically with different agents we work with today? Well, you think about it. Hey, this is Lance from LangChain. You might have heard this term, only relevant tools into context. Now, finally, I want to talk about knowledge. RAG is a huge topic. You can kind of think about memories as a subset of RAG, but RAG is, of course, much broader. We often want to augment the knowledge base of an LLM with, for example, private tokens. The code agents are some of the largest scale RAG apps currently, and I actually thought this post from Varun, the CEO of Windsurf, was quite interesting. He talks a bit about the approaches that they use for retrieval, and the real point is it's quite non-trivial. So, of course, you're using indexing and embedding-based similarity search as a core RAG technique. But then you have to think about chunking. So they, for example, do AST parsing to chunk along semantically meaningful code boundaries, not just random blocks of code. So that's kind of point one. But he also mentions that pure embedding-based search can become unreliable, so they use a combination of techniques like grep, file search, knowledge graphs, and they use an LLM-based re-ranking on top of all of these. So when you look at knowledge selection in popular agents, for example, like the code agents, this is highly non-trivial, and a huge amount of context engineering goes into knowledge selection. So we talked about writing context, we talked about selecting context. Now let's talk about compressing context. This really involves retaining only the tokens required to perform a task. So a common idea here is summarization.
I see. So I think instead of focusing my engineering work on just compressing text, I need to first build the infrastructure or the logic for saving context outside of the context window, and then using that context in a way that is relevant to the work of the LLM. So not just pulling all the context that I have. So building selecting of the context, and then I can work on compressing the context which is needed, right? So yeah, I think the first two is really important in building this context engineering workflow. Basically building sort of a context engine, right? But once that is done, I mean, we already have the infrastructure set up for a lot of the compressing, right? We have the hard prompt pruning using the self-information scores already pretty much built, right? But that's just one subslice in this whole issue, right? Which I think is much more than just, context compression. There's so much more that goes into that, goes into context engineering. And I knew this from before, but it's good that I just got a little refresher, right? Yeah. So after the context compression, there's also isolating the context, and that's actually something that we're already doing, right? I'm already doing that isolation of context by creating a multi-agent approach, right? We have the supervisor pattern, which creates two separate agents, and it does that. I made the code in this specific way by using the base agent template, right? This base agent template, which includes a class over here, is basically what allows us to essentially allow multiple agents to be created. So right now we only have a legislation finder. However, I'm actually going to be rebuilding this so that we will have two separate agents. We're going to have a lead researcher agent and then a researcher agent, and then within the pipeline itself, right, within the pipeline itself for the NV local, this pipeline itself, which has these nodes, what we're going to do is this will first get the content retrieval right from the Oh wait, never mind. So in the NV local, yeah. So we're first gonna find the legislation, right? And you do that through the legislation finder. I'm gonna change this name to run discovery agents, and that, or run researcher agents, and then in this specific work, right, in this specific file, there's going to be the multi-agent approach, right, where you're gonna basically take the lead researcher, and then that lead researcher is going to spawn researcher agents to do work for them, right? So that's going to be great to do in terms of implementation wise. And yeah, I think that's what we're going to be working on. We also have a note taker, but I'm not sure why it's a... Yeah, the note taker is like something that is like a chain. I don't want that. So in here, I guess, first of all, I'm gonna close this issue. I don't really need this. Okay, yeah, this is good. Improve context engineering of AI workflow. Once the multi-agent architecture has been fully built, so yeah, we started off by just wanting to do more work in understanding this paper, but I feel like that's kind of low leverage now. I think just going through the context engineering of this paper, this specific blog, would be much more better. Yeah, so I think this over here is like a much more useful resource than what we had before. Okay, but this is going to be improved context engineering for AI workflow. Once the multi-agent architecture has been re-implemented, right now it's fine. I mean, it works, but I feel like the way it's being built is not the best or most optimal approach. Oh, so wow, we could just use a supervisor like abstraction. Alright, so Okay, so here it's saying just make your own thing instead of using the create React agents. So a lot of documentation today and just getting everything set up.
everyone, this is Evgeny, and I welcome you back in the next video about line graph advanced series. Today we're gonna continue talking about supervisor architecture, and I will show you how it can be constructed under the hood. So join me at this using line graph primitives and not this high-level API. But before we're doing this, so we have the communication channel, and we can check the there's experience, but define the communication channel. Like we have a supervisor, we have agents, and they need to communicate somewhere. And from the previous videos, you know already that the tool name is handoffs. So the way how different agents can communicate in line graph using handoffs. And handoffs work normally as a tool. So we have to create specific tools and provide them to agents to allow them to communicate to something else. I'm going to reuse the same function from previous lessons. So we have this create handoff tool, and this one, it takes the agent name, it takes some description, and finally it creates the handoff tool, which we can reuse. And there, since it's a tool call, we are marking with a tool here. We need to create a tool message as a response to the tool call. And the important thing here, okay, we are providing some content, we are providing the name, and then we have to put the same tool call ID. So there's a pair of tool call and tool call response. And finally, we are returning with a command where we are saying that, okay, the command is go to specific agent name, and this is on the scope of all the graph.
Okay, right now I think we should just keep it high level. But yeah, that is something that we definitely need to do. Cool, so I guess now I know I don't really want to use this compact prompt, and instead what I need to do is work on the holistic context engineering process of figuring out ways to properly write context. I already have that, but just making it more established. So the writing of the context, specifically by using some sort of like file storage system or an in-memory database, maybe through SQLite, to have the Scratchpad approach, right? Or we can even use the states, right? We have states in LangGraph. So properly formatting like a note taker state to allow that to happen, I think that's a really good approach. Yeah, so that's stuff that we need to talk about and worry about later. And then yeah, retrieving from Scratchpad, we need to figure out that. Most likely using some sort of like RAG approach or an index approach. Compressing, we already have that through hard prompt pruning, which is going to be very useful when we're doing handoffs from like researcher to lead researcher, or the lead researcher to the researcher. And then isolating the context is already done because we are partitioning the context within multiple agents. So each of these researchers will have separate context windows which are specific to their research tasks, and that's all being managed, the actual delegation of these tasks, by the manager or the supervisor, which is your lead researcher. That's his only job. His only job is to basically create these lead researchers, create these tasks, delegate them to researchers, and then get back a synthesized summary of all of the research that has been done. Yeah, that's pretty much it. And it will also, I'm not sure if I wanted to like stress test it yet. Yeah, we'll look into that. But for now, it's good that I know at least this bit over here. So let me actually go here. This whole flow should be implemented by the time this issue closes. Yeah, so this whole thing will be implemented. Alright, that's pretty much it. Bye.